All right, so now that we've talked about what the titration curve looks like, let's try some calculations. Let's keep in mind that acid-base is going to be easier when it's strong and strong. So our objectives, we'll perform calculations at various points along the strong acid, strong base titration curve, at the start of the titration, at the half equivalence point, at the equivalence point, and after the equivalence point. A titration is carried out for 25 milliliters of 0.1 molar NaOH with 0.1 molar HCl. What is the pH at the following volumes of acid added? Then we have a nice laundry list here: 0 milliliters, 10 milliliters, 12.5, 25, 37.5, 39 milliliters. Whenever you find yourself looking at a titration problem, it is always a chemical reaction. So start with the balanced chemical equation. I'm going to put the balanced net ionic equation because I'm lazy. But either way, this is an acid-base neutralization reaction. We have a strong acid and a strong base. We'll have H plus OH minus goes to water. Hooray. Second thing I want to know for any acid-base reaction titration is, where is my equivalence point? Everything else we do is going to be based around that point. So we're going to start by calculating moles of titrand, or analyte if you prefer. So we have 25 milliliters and 0.1 molar. We're going to convert milliliters to liters, and we get 2.5 times 10 to the negative third moles of OH minus, because we have full dissociation. It's a strong base. All right, so now we know the number of moles at the equivalence point, and then we need to find how many, at the equivalence point, moles of OH minus is going to be equal to H plus. We need to figure out the volume. If we're really observant, we notice that these are both the same concentration, so 25 is going to be the equivalence point, but let's assume that they aren't the same concentration, so we would do moles of OH minus times the mole-to-mole ratio from the balanced chemical equation divided by the molarity of the acid. And lo and behold, we do in fact get 25 milliliters. So pH there is going to be 7, because this is a strong acid, strong base titration. So now we're going to split this into two parts, and we're going to do stuff before the equivalence point, and then we're going to do stuff after the equivalence point. All right, so let's start with the easy one. Let's start with 0 milliliters. With 0 milliliters of HCl added, the only thing that the pH is due to is the concentration of the OH minus, which for a strong base is fully dissociated. The concentration of the NaOH is equal to the concentration of OH minus. So we can just use the 14 minus log of OH minus, which gives us a pH of 13. We're starting this titration at a pH of 13. All right, so now let's go on and do the 10 milliliter and 12.5 milliliter points. Okay, a titration is carried out. We know that 0, we're at 13, so let's find out what happens at 10. At 10 and at 12.5, we know that the amount of stuff in the flask is less than the amount of stuff that we've added from the burette. So the titrand is greater than the titrant. As a result, we can make a little BCA table, right? So we've got H plus OH minus. Really poorly written, but I hope you get the point. Going to water. And we are not going to bother calculating anything with water because it's not part of our equilibrium equation and it's irrelevant. We're going to do a BCA table. So we calculated that we have 2.5 E negative 3 here. Right, and if we do 0.1 molar times 10 milliliters, convert that, right? We get 1.0 E -3. And we're doing BCA, so this is the before. Our change is to subtract off the 1e, -3 from both the H plus and the OH minus. Not the most legible thing I have ever done, but hopefully we're getting the point. And then our after is going to give you 0 for the H plus, which is what we expected, and 1.5 E -3 for the OH minus concentration. Okay, so let's show that with slightly less awfulness as far as writing. And then if we want to find the pH, we do the same 14 minus the log of the OH minus. But in order to do that, we have to get it into concentration. Okay, so to find concentration at this point, you know that you have to take your initial volume of titrand, add the titrant that you added, you get 35 milliliters or 0.035 liters of solution. We take our moles over our liters to get molarity, and that's 0.043 molar. And finally, we plug it into the negative log equation and we get 12.63. So we've now done 2 out of 3 of the things before the equivalence point. Let's do it again. So again, we know that at 12.5, our titrand is greater than our titrant. So I'm not going to write the BCA table again, but we would start with the 2.5 times 10 to the negative third moles of OH minus, and we would subtract off 0.0125 times 0.1, and we get 1.25 times 10 to the negative third moles of OH minus left. Now we need to know the total volume at this point, so it's 12.5 plus 25, which gives us 37.5. We convert that into liters, and then we calculate molarity. So we have 1.25 times 10 to the negative third moles divided by 0.0375 liters to give us 0.033 molar OH minus. At this point, we plug it into the 14 minus log of 0.033, and we get a pH of 12.522. So we can see that our pH is quite steadily going down as we add acid, which is what we expect. At this point, let's try the things after the equivalence point. So remember, the equivalence point, the pH is 7. So for both the 37.5 and the 39 milliliters of HCl added, the titrant is now greater than the titrand. So in other words, we're going to have excess HCl. We can do a BCA table for this, just like we did before. Okay, so we've got our HCl plus our OH minus. I'm not going to bother writing water because, again, it's irrelevant to this process. Okay, and if we do 0.1 times 37.5 converted to liters, we get 3.75 times 10 to the negative third moles of H plus. We notice now, hey, OH minus is smaller, so we subtract off the entire amount. So one-way reaction, we're getting rid of stuff. We're going to do that on both sides. Here, both for the OH minus and the H plus. Let's pretend that looks like a 3. And we get 1 point. Ugh, that's illegible. Like extra super illegible. Let's try again. Okay, So 3.75 minus 2.5 gives you 1.25 E negative 3. And we have 0 OH minus left. Okay, again, we've got to get that into molarity. So we have 25 plus 37.5, which gives us 62.5, or 0.0625 liters. We put our moles over our liters, and then we put it into this equation, because now we have a concentration of H+, we just need to do the negative log of the thing, and we get 1.699. All right, so let's try it again, but for 39 milliliters. We're going to do our amount of HCl minus what we started with for OH minus. We have 1.5 times 10 to the negative third moles of H+. We find our total volume at this point in time, which is 64 milliliters, or 0.0640 liters. Then we find molarity. And so we take the negative log of the moles over liters, and we get a pH of 1.630. So did we need to do that iteration? Not really. We already knew how to do it, but it doesn't hurt. It tells us some things. It gets us to recognize the pattern. To summarize, whenever you have a titration equation, write the balanced chemical equation. Determine the equivalence point and the half equivalence point for your titration. The half equivalence point doesn't matter so much for strong acid, strong base, but for weak acid, strong base, it's going to be clutch. Use your BCA tables to determine the moles reacted and the moles remaining. Calculate the molarity of whatever species is left. And be careful with your pH versus pOH calculations. So use the correct one for whatever situation you are in.